Okay, hi everyone. Can you hear me? Give me a check mark if you can hear me. Good, thank you, Lauren. Great. Well, I want to go ahead and get started. This endeavor usually takes about 2 hours, so it's my intention to get done in about 2 hours, plus or minus a little bit. Effectively, what I like to do on this last day is to go through the entire book. I have, if you can see my, you should be able to see me here in the corner and then see my book down in the main part of the screen down here. So essentially what I have is I have a full, this is the full textbook that we've used in this class. This is the McClave and Sinkage. And I have a full textbook full of notes that I'm going to go through and essentially talk through all of these notes that I have here, because I find this to be useful in helping people understand the material right before we take the final. And I have a game to play called Guess My Test, which is pretty cool. Let me just take a poll. Is there anybody that wants to just do the game, which is essentially a skill review of all the tests we've done, and then leave for the night? And if so, we can do that now. Or if you want to listen to me ramble on through all the material for a little while and then do the game, then we'll do it in that order. So let me just raise your hand if you are interested in just playing the Guess My Test game and then leaving for the night, which is perfectly fine. I just want to make sure I don't, drag you along for a long time here. Okay, nobody? Okay, great. So I think it makes more sense to go over the material first, so that's what we'll do. So we have covered a lot in this class, a lot of material. It's a dense class. I know it's a dense class. We started by talking about the different types of statistics, and there are two. There are descriptive and inferential statistics. Descriptive statistics is essentially just routine algebra, calculating things like mean and standard deviation and variance and things that you can just obtain by just doing calculations, routine calculations, algebra types of things. Usually we use Excel to quickly run through a statistical calculation. Those are descriptive statistics, okay? Inferential statistics, the first thing that you should think of when you think of inferential statistics is probability. Because inferential statistics, the whole goal of it is to take a sample that is representative of the entire population, but to take that sample and then ask it to make an inference about the entire population. And of course, we're making an inference, which is a fancy word for a guess. And anytime we guess, we have a probability that we could be wrong. So kind of intertwined with this idea of inferential statistics is the idea of probability. And that probability, which we learned, is called a confidence level, okay? So just a review of some vocab words. Experimental units, that's the object about which we are collecting data. It might be a person, a thing, a transaction, or event, or some other thing. Usually it's a person or a thing. Population is the set of all units. Usually, as we've seen, usually the population is kind of this nebulous idea that we don't have direct or realistic access to. And so that's when the idea of inferential statistics comes in, and we pull a sample from the population and we ask that sample to represent the population, okay? There are 4 parts of a descriptive statistics problem: the population or sample, the variables, any types of summary tools in our analysis project. That was the histograms and the data tables that were produced by SPSS, and then identifying patterns in the data. That's where you would look at the Platy-Kurtic numbers or skewedness numbers, things like that. In inferential, you're adding one more. You're adding in a measure of reliability. So you still have the population, the variables, the sample, population or sample, and we're making an inference instead of having summary tools. But the thing that is not included in descriptive that is unique to inferential is this measure of reliability. So an example of that would be if we say that we're taking a 95% confidence interval, that is the measure of that reliability is that if we run the same thing many times, 95% will capture the true mu. That's a really good, straightforward example of a measure of reliability. So if somebody asks you, how reliable is this number? Well, 95% reliable, because if I run the same calculation a zillion times, 95% of them are going to agree with this. So that's, and I like to say this again, I know I probably harp on it too much, but confidence level does not mean how confident you are in the buttons that you pushed or the formulas that you used. Confidence level means exactly what I just said. It means that if you run the same calculation many times, then you're gonna get agreement at that level, that number of times, that proportion of the calculations are going to agree. It's never a reflection on your personal abilities as a statistics person. Okay. Quantitative and qualitative, I'm hoping that we've gotten this all down pat now. Qualitative is just categorical. Quantitative is numerical in value or occurring on a number scale, like the integers or the real numbers. Okay. I think all this is good. Are there any questions yet? Just speak up, by the way, because I don't have the chat box or the participant window open. So if you need something, just speak up and interrupt me, and that's how I prefer to do it. So when we're getting into the actual meat and potatoes of this, let's talk about qualitative data. Okay, qualitative data here. So this is the categorical kind. A class is one of those categories. The way that you're dividing up your data, it's kind of the bin into which you're deciding what goes where and what gets separated out and put somewhere else. The class frequency is the number of observations in that class. So it's just counting up the number of things that are in that bin. And then the relative frequency is simply turning that into a percentage, where you take the class frequency and divide by the total n. So it's just taking that cardinal number and turning it into a percentage. Rather, that's the class percentage. That's the class percentage, but it's the same thing. We just take that and multiply by 100. I'm assuming that everybody in here can kind of switch between those ideas in their head. These we should know: bar graph, pie graph, Pareto diagram. Pareto diagrams are neat. We didn't really do a lot with them in this class, I don't think, but I want to remind you of the difference between a bar graph and a histogram. So a bar graph is for categorical data, qualitative. Histograms are for quantitative data because the x-axis is a number scale. So that's why the bars touch, because the number scale is continuous in between the bins. Okay. Then we started talking about I'm assuming also that everybody can calculate a sample mean. So we use X bar for sample mean, mu for the population mean. Median is a capital M for the sample and is eta for the population. And we started talking about how those relate to each other. We talk about this word skewed. Well, skewness looks like this. When it looks like a bell curve that's been kind of like it's a lump, maybe I don't know, a pile of putty or something, and you shaped it into a nice bell curve, and then you took your hand and you pushed it all to one side and kind of smudged it over to the side. So that's what skewness would look like. In this example, rightward skewness, I want to just note this. This is really sometimes confusing when you're talking about nomenclature. So right skewed does not mean that the lump has been shifted to the right. It means that the tail is longer on the right-hand side. So if you notice, this tail is longer going out this way. That means it is right skewed, okay? Not that the lump is shifted on the right. It's the opposite. So if the lump is on the left, that's right skewed, vice versa as well. And the reason for that is that the median falls lower than the mean. That is how the bulk of the distribution gets moved over that direction, is because the median is pulling it down. The exact opposite happens for left skewed. When the median and the mean are identical, then you have symmetry, which is a standard normal curve. There's the diagram for left skewed. It's the exact opposite. Okay. So I would also recommend at some point in your life, and I probably should do this myself, and I still have to look it up sometimes, but try to just memorize the formula for sample variance or sample standard deviation, same thing. Try to remember it, because it's always embarrassing for me, you know, as a stats teacher, when I have to go back and look at the formula for that, and I still, after all these years, have to do that. So I recommend just giving yourself a little brain exercise and trying to memorize it, and then you can impress all your friends. Of course, S is the standard deviation. S squared is the variance, and these are sample measures. So if you square root both sides, you'll get the standard deviation. Okay, just remember that. Okay. Now, this is where we started getting into this idea of population versus sample. And if we're relying on samples to do so much for us, exactly how good is that idea? So we realize that S will go as sigma. Again, S is for the sample, sigma is for the population. These are standard deviation measures here. Standard deviation measures. But S will go as sigma because of the central limit theorem, and that's the idea of the sampling distribution that we started getting into. So a lot of times we don't know sigma, but we need it, and so we can use S as a reliable substitute if certain parameters are met. Okay. So just to remind ourselves of that. Okay. Outliers. There are two ways of detecting outliers in a sample. One is with using the interquartile range, and the other one is using a z-score. It really just depends on maybe what's more convenient at the time, but both are reliable. Both will get you to about the same place. So typically, three interquartile ranges. And interquartile, so if, we didn't really spend much time on this, but quartiles, It's when you divide a data set into 4 equally sized bins with equal numbers of n over 4 data points in them. And so the interquartile range is the dividing mark for the third quartile and the first quartile subtracted. So you get the range, the difference between the first quartile and the third quartile. So 3 times that number as a plus or minus, that is going to give you your barriers, your boundaries for what you would consider an outlier. Now, between 1.5 and 3, those are suspect. 3 or outside of plus or minus 3 are highly suspect. A lot of times what you'll do is you'll also use like two interquartile ranges, just to, you know, that's a good ballpark, kind of falls in the middle here, and it'll give you a good starting point to determine if something is an outlier or if your eyes are just playing tricks on you.
Alex, what page is that on? Sorry.
Oh, that's 89.
Okay, thanks.
Sure. That's 89. A lot of times box plots, I hate box plots because it has to do with how you view it. And you know, perception is subjective, which is why we have mathematics, because it's not subjective. But sometimes these graphs are, and I was talking to a lot of people during the analysis project, and they would ask me for help in interpreting a QQ plot. And I mean, the QQ plot is helpful, but the way you interpret it and the way I interpret it might be different. So in order to really get at the real hard statistical conclusion is to look at something numerical and being able to gauge that numerical result. So that's why a lot of times when I'm looking at a QQ plot, I want to look at the residual, the R squared, the residual correlation, because then that gives me an actual number to go off of, and it's not, you know, where my eyes think the dots are falling or whatever, you know. So so I do recommend going with z-scores if you can. If the z-score of your suspected outlier is greater than 2, it's possible. If it's greater than 3, it's definitely an outlier. So that's usually the most reliable and conservative measure that you can do to detect outliers, is a z-score greater than 3. Okay, and if you think about it, possible outliers, well, what would be greater than a z-score of 2? Well, it would be, that would put you almost at that 2 standard deviation mark. So that's going to be, you know, the bulk of the data, yeah, is going to be in there. So it just to you know, correlate what we're doing with what is kind of intuitive, I think is important. Okay, so we're going to get into probability. Probability, I know, is kind of a pain for a lot of folks, so let's try to rectify that. So probability is basically just a really fancy exercise in percentages, right? So you're essentially, all of probability boils down to specific divided by whole, or you know, desired outcome divided by total possible outcomes. Some kind of, I mean, that just turns it into a percentage or proportion. So basically all of probability is that. Now, getting that specific or whole components may be easier said than done. But go back one page here. So consider an experiment of tossing, oh shoot, oops. I have this huge desk and I've still managed to fill it up with crap. So I need to get more diligent about cleaning my desk off. So consider the experiment of tossing two unbalanced coins. Because the coins are not balanced, their outcomes are not equiprobable. So let A be the event of observing exactly one head and B being at least one head. And so here are our sample points. So we're tossing two coins, and these are the probabilities here. They're not all the same because they're not balanced, okay? So looking at each of these, 4/9 is that specific over whole. It's saying that specifically there are 4 ways to get two heads and 9 ways to get possible outcomes. So that's just a very simple example of that in the core level. And this is important to remember. Probabilities should always be interpreted as happening in the long run, because if you just take an experiment of one trial, it's very likely that you're going to fall into one of the more minority possible outcomes because you've only done one trial. But the idea of probability is that if you run it over and over and over again, in the long run, the numbers will fall out into this kind of distribution. Okay, so we have the combination rule. This is how you calculate a combination. Something else I kind of recommend committing to memory. I too often have to go look it up because I just can't remember because it's been too long since I used it the last time. This is also something that you can easily put into Excel to calculate instead of doing all these factorials yourself. Okay. Let's see. Okay, so now let's talk about, just as the word implies in English, a union is a joining of two different things. So if I was to join, you know, two separate groups that had no overlap, the union is the new collection of all of everybody that I've made. The intersection, just as its name implies, just like when two roads cross each other, the intersection is that little tiny square cross section in the middle where they both exist for, you know, a few square yards. So just as in mathematics, we have unions, which are the collection of all of everybody. In this case, this circle is A, this circle is B. The union is everybody. The intersection is just where they cross over. It is perfectly possible for an intersection to be empty if there's no overlap. Complementary events basically means that the probability of something happening and the probability of it not happening is 1, which again is logical. I like to approach the probability as a very logical endeavor. So the complement of something is simply just putting the word not in front of it. Don't make it any more complicated than that. So, you know, you may think logically that, well, the opposite of, I don't know, the opposite of, the complement of going to the grocery store today would be going to the grocery store tomorrow, but that's not the case, right? On a practical level, if you don't go to the grocery store today, then yeah, you may need to go tomorrow, but that's not the probability complement of not going today. The probability complement of not going to the store today is simply that I go to the store today, right? So I just put the word not in front of it, or I double not and take it out, just a simple negation. So the idea of a rule of complements is that the probability of those two complementary events summed together has to be 1, because there's a 100% chance that something either is going to happen or it's not going to happen. Okay, so the additive rule of probability is pretty interesting. The probability of the union of two events, the union is the collection of all of everything, right? the probability is A plus B minus the intersection. Now, why do we subtract? Why do we subtract the intersection? We're adding A and B. Why do we have to subtract the intersection?
That's A and B that we're subtracting.
Right.
Right.
But logically, why does that make sense, though?
So we don't count it twice?
Yeah, otherwise you're double counting everything, because everything in the intersection exists in both A and B. So if you just added A and B together, you've double counted those entries that are in the intersection. So you've got to pull one of them out to compensate for that. Good job. Good job. All right, so let's see here. Okay, so now we're in probability distributions. This is, I think, one of my favorite parts of teaching statistics, are probability distributions. So a probability distribution is just what it sounds like. It's a distribution, just like the data is distributed, but the probability distribution is a distribution of the calculatable parameter of interest that you might be interested in. So this is an example of, like, let's say our parameter of interest is a mean. So if I run that mean and calculate that mean a bunch of different times, I'm getting a new set of data, right? I started with a set of data. I can calculate the mean because that's just routine arithmetic. So I calculate a mean and boom, I get a number out. And then I do it again and I get a number out. And I get all of these new numbers. That's a new set of data. And the way that data is distributed is a probability distribution. So now, again, the idea is that we're pulling a sample each time. That's why we're getting a different number each time. But if you added up all of those probabilities, you're going to get one. All the probabilities for all those values, okay? From X, whatever X is our parameter of interest, works the same for any of them because of the central limit theorem and calculus. So the mean or expected value, the mean, of course, is mu. We're very familiar with that. The expected value is this E of X. They mean the same thing. They're synonymous with each other. Sometimes you use one word because it's more linguistically appropriate than the other, or more theoretically appropriate. But that is essentially this expected value, or mu, is simply the sum of each of the x's multiplied by its probability. So all that is it's the same thing as a weighted average. Like we all calculate grades here. That's exactly the same thing as calculating a weighted average. Okay. And I recommend so this flows right into variance. I recommend using this form if you need it on the exam. It's much easier to plug things into and to just kind of rationally get your head around. So I recommend using this right here if you need to for the exam. Okay. This is on page 175. So, and that's sigma squared. Isn't that cool? I think that's cool.
Can I ask a stupid question for clarification?
Sure.
Right there where you've got the summation x squared, probability of x minus mu squared. Is the mu squared is being subtracted from the summation? It's not part of the summation, right?
Correct.
Okay.
Yeah. You're summing. This is giving you, I really need to organize my desk. All right. So this part is giving you the, and it's different because the x is squared, but this is essentially giving you an expected value. That's what that is. And then you're subtracting mu squared to compensate for the x squared.
And that's what I thought. I just always get like overthink where parentheses need to be. So
okay, yeah,
double checking.
I gotcha. Yeah. Okay. So did I say that? Oh, by the way, back on page 158, this is a great chart. I think there's even a scan of this floating around on D2L. If there's not, I can email it to you. This is a great flow chart for studying on 158, for studying the different formulas for different probability situations. I like this a lot. So if you haven't gotten that, let me know and I will send that out to you. I have it already scanned. So let's do some Chevy shove. Okay, probability distributions again here. So we learned two different rules that govern how these distributions behave. One of them is called Chevyshev's rule. This applies to this will work for anything. It's primarily used for non-normal or non-mound shaped, non-symmetric. This is mound shaped and symmetric is empirical. This will work for anything, but it's primarily used for things that are not mound shaped and symmetrical because this one is a lot more accurate. If you were to take a mound shaped symmetric distribution and calculate things with both of these rules, this is going to be more precise. It's less conservative because the shape of the distribution is predictable. This one would be less precise, which, you know, if you can easily trade it out for a more precise calculation, I don't know who wouldn't. But the nice thing about that one is it doesn't have to be mound shaped or normal at all. It can be whatever. Okay. So study this. That's that annoying formula for binomial probability. I just say study it because I've seen a lot of students get tripped up on it and they don't plug the right things in or they forget, I don't know. Anyway, just make sure you're familiarized with it so that if you have to use it at some point, it doesn't throw you completely out of the guardrail, you know? Panic with it now, don't panic with it during a test. Also study this because this, I have seen students who are doing well with everything and they forget this for binomial. And I don't want you to get stuck in the middle of an exam and think you're calculating variance a certain way, but you forgot that it's binomial and you calculate it this way for binomial. So just take note. A lot of students have trouble reading a binomial probability table, and you know, that's understandable. So the table is cumulative by column. So columns, you know, cumulative by column. So that is why you subtract the entry above if you just want a specific value. So when I say cumulative, I mean that if you start here and you start to go up, you're eventually going to hit 1. And the number, like in this position, the number here includes the number here. So if you just wanted that, what is that, a 4? Then I would take 0.633 minus 0.382 because I want to get rid of all this crap up here. I just want the 633. No, rather, excuse me. I just want the value for 4. Okay. So the difference there would be if you wanted the probability of exactly 4 blankety blanks happening, that would be 633 minus 382. If you wanted the probability of up to 4 blankety blanks happening, then that's just the 633 because it already includes all the stuff that came before it. It already includes 1 blankety blank, 2 blankety blanks, 3 blankety blanks. It includes everybody, okay? Everybody that came before it. This is a great, I just would say read all of this stuff right here on page 189 if you're having trouble understanding how to read a probability, a binomial probability table. Okay. And that's for anything that's a BRV, a binomial random variable. Binomial random variables are variables that just have 2 outcomes each time. Each time you run a observation, it can be 1 or 2. That's what makes it binomial. A lot of times they're yes or no, or success or failure observations. Those are the most common. Trouble reading z-tables. Oh, in case you're ever curious, I don't know, we didn't ever actually cover this in the class. This is what a probability density function actually is if you're interested in the mathematics behind it. So we didn't really cover that, but it's here. This is for the normal, this is for normal curve. So if you were looking for the function that generates this shape, there it is, it does exist. That's on page 196 in case you ever are interested in some light reading. So 197, a lot of folks have trouble reading z-tables, either forwards or backwards. So we can go over some examples of that, but I just want to remind you that the entries in a z-table give the probability between 0 and z. And some of them, and that's why it'll always have a little picture here to show you how it is set up. Because as I've said before, there are some z-tables that are read from the far left and they already have this 0.5 added into everything. And the one in this book is just read from the middle, and they're just expecting you to add 0.5 if you need to read it from the far left. Arguably, these are a little bit more handy, but they're also a little bit more technical. Okay, calculating a z. I hope everybody could do that in their sleep by now. X minus mu over sigma, or X minus X bar over S. So the binomial random variable, this picture does a great job of it. The binomial random variable looks like this stack of, it looks like a histogram. And at some point, it actually approximates the normal curve. So if you want to do that, and this is on 221, if you want to tie over binomial random variables and normal, hashtag Z, you're going to do that using a couple of approximations here. So you'll have the interval is NP plus or minus 3, again 3 sigma, that gives you the 90, this is a 99.7%. NPQ is again how you get the sigma for binomial. So we're just plugging in NP for mu and the square root here for sigma. Go to your binomial table, and the Z value, this is a correction here. We have A plus 0.5. A is the correction for continuity. The A plus 0.5 just gives you this little bump here for these little dimples that are sticking out over the normal curve because they are not located where they should be. They should be chopped off and then plugged into one of these empty spots where it's under the curve. So that's all that's doing. If you're curious, it's 0.5 because we're assuming that the bins are 1 and half of it's inside the curve, half of it's outside the curve. So that's where the 0.5 is. Central limit theorem, I talked about it a little bit before. It really is key. It allows us to do everything we do in here. So when n is sufficiently large, the sampling distribution of the sample parameter, x bar, s, whatever, will be approximately normal, a normal distribution with mean of mu, and the standard deviation of sigma over square root of n. That's that corrected standard deviation that we see a lot, okay? Obviously, the larger the sample, the better, because you're essentially taking a limit as n goes to infinity, and that will approximate, that will get you closer to the real thing. So confidence interval for mean using z is, this is for z, this is for, excuse me, for large samples. So we have x bar plus or minus 1.96 times sigma over the square root of n. That's again, that sigma over square root of n is that corrected sigma, the sigma for the sample. So that's how you would calculate a confidence interval, excuse me, for a mean. This structure shows up again and again, so just keep that in mind. Shows up again and again for confidence intervals. I've said this before, a confidence interval doesn't mean how confident you are, it means how confident, or rather just means how often that number, that interval is going to reoccur if you, or not reoccur, but how many of the intervals will capture the true value if you did it a bunch of times. So really that is how confident you can be in your work, because that's as good as the numbers are going to be to you. Okay, alpha is simply the area in the tails. It's outside of the confidence interval. That is an important concept. The value of z sub alpha is defined as the value of the standard normal random variable z such that the area alpha will lie to its right. So z sub alpha is just the cutoff point for alpha. So what that is saying is that whatever your alpha level is, you can have anything as your alpha level. Whatever your alpha level is, let's say it's there, z sub alpha is just taking that alpha number and then turning it into a z number. That's all it is. So maybe alpha is 0.05, but that doesn't mean anything in terms of z, in terms of the normal curve area. So we just take that and convert it over to a z value, and that is what z sub alpha is. It's essentially just a critical z value. Another book that I teach from calls it z star, and they just use the denotion that a star means that it's a critical value where the threshold is, where things cut off. Okay, so of course, if n is under 30, then we go to t, which is more reliable. T is a family of distributions. It's not one distribution. A lot of times it's a good idea to remember how you calculate z or t. This is 265. If you're going to do this by hand, this is how you do it. Here's the z statistic and the t statistic, which are the same. You're just replacing sigma for s. Now, sometimes you want to calculate it by hand. A lot of times I don't want to calculate it by hand, but if you have to or if you want to, that's how you do it. Manually calculate t. 265. Okay. This is the family of distributions. We've talked about it. The lower your n is, the flatter and fatter your t is going to be. So the more n that you collect, which is logical because why do we have t in the first place if n is too small? So if n is under 30, you've got this t situation, but as you're getting closer and closer and closer to 30, this distribution is going to just raise right on up there and get right on up there with the normal curve. So the thinking is that after you hit n equals 30, then it's the same as the normal, and in the reality, it is the case. It is the case. But that boundary of 30 is arbitrary. This book chooses 30. The other book I'm teaching out of right now, the David Moore book, that chooses 100, I think, or 50 or something as its cutoff. I can't remember at the moment. And then there's some really conservative statisticians that say, I only want to use Z if I'm over 100. So for anything less than 100, I'm only using T. And even some more conservative statisticians only use T for anything because they know that it will err on the conservative side of the calculation. And we're talking about microscopic parts of a decimal point at this point. But, you know, you can have a nice heated argument with plenty of folks over coffee if you want to about that. So this is a really good example. If you look really closely, okay, see how Z and T just vary, especially out here in the tails where the critical alpha values start to happen. These little tiny deviations, it may produce very small changes in your output, but depending on your application or use of the numbers, that may be a big deal. You know, if I was designing a space capsule or designing, you know, one of these spaceships with NASA, I probably would use only T because I could more reliably rely on that. So just small little differences right there is what we're talking about. But still, a lot of people are happy to have an argument with you about that. So how do you deal with mu if you got a small sample and you got T? All right. So this is how you get a confidence interval for mu. It's just if the sigma is known, you use if the sigma is known, you use sigma and Z, and it just treat it like a Z. That's fine. If it's unknown, you use S, and you substitute in for T. Okay, so that's how you do that. Again, remember the T distribution is based on n-1 DFs. Always has to be random and normal. Random and normal. Always has to be random and normal. Okay. Making some good time here. So now we're going to change a gear totally. And instead of thinking about a mean or a variance as our parameter of interest, we're now going to think about proportions as parameter of interest, as the thing that we're interested in learning about. Okay, the question needs to be answered by a proportion instead of a mean. So that is, the mean of the sampling distribution is p hat. Wait a minute. I'm sorry. P hat is the proportion. Excuse me. P hat is the proportion. That's the symbol this book uses. So it's the number of, it's again, goes back to probability, specific over whole. It's the number of people that you are interested in over the total number of people in the pool. Okay. So again, the sampling distribution behaves just like the sampling distribution for mu. The standard deviation is pretty similar. it's PQ over N. Q is simply the complement of P. And you have to make sure that the samples are large enough. Otherwise, the calculation, the behavior of this becomes shaky. So you just check N times P hat and N times Q hat, and make sure they're both higher than or equal to 15. Okay. A large sample confidence interval for P is going to take on the same type of format as we've seen before. So we've got our point estimator, P hat, plus or minus Z hat, or excuse me, Z, critical value of Z for one tail, times this corrected standard deviation. So, and again, I'm just pulling that standard deviation from right here, so there's no trickery going on. You can approximate it with the P hat and the Q hat if you need to. And this is only going to work, again, if those numbers are larger than 15, if the NP hat and the NQ hat are 15. If not, you use Wilson's adjustment, which is on the next page. And this is on 278. So unless N is extremely large, this procedure performs poorly when P is near 0 or near 1. So this is came out by some person named Wilson in 1927. This is how you correct for that. You use this P tilde and number instead, and P tilde is just this X plus 2 over N plus 4. Okay, so that's how you adjust it if your numbers are not large enough, if your N is not large enough. So remember to do that, because that will change your answers. Hopping into 5.5, excuse me. Hopping into 5.5, determining a sample size for mu. So this is going back, I think the problem in the homework was the aluminum can problem. And essentially all this does is it takes exactly what we just did, but it rearranges it so that it's solved for N. It rearranges it so that it's solved for N. Okay. So just keep that in mind. That's on page 283. Oh, sigma is usually unknown, but you can approximate it with R over 4, where R is the range of the highest value to the lowest value, the range divided by 4. Confidence interval for P, sample size, same kind of a deal as before, but just for P instead of for mu. So the note here is that because the product of PQ is unknown, it can be estimated by maximizing that product. If you just think about it as what's the largest number I can get out of P times Q, and that's 0.25, because that will happen if P is the highest and Q is the highest, I get 0.5 for each of them, and the product is 0.25. So that's how I make that value largest, which is what I would want to do to be conservative if I'm calculating an N. So that's why we just plug in 0.25 for that PQ value right there. Okay. That's just a little, algebraic trick to make the number land on the large side. Okay. Confidence interval for variance. This one tripped up a lot of people on the homework. Confidence interval for variance. This is saying that the variance, the population variance is in between these two numbers. Now the numerators are the same. The denominators are just chi-square values. And I sent out a chi-square table for everybody. So you look at the chi-square table in two columns. You look at it in two places. They're complements of each other. One is the chi-square of alpha over 2, which is just the chi-squared of your one-tailed cutoff point. And the other one is the complement of that. So it might be 0.95 and 0.05, right? Because those are complements of each other. So you just look in the right columns. You'd match up the two columns that you want. Or rather, you pick the column that comes from your confidence level, and then you just look for its complement by subtracting from 1. And then you've got your two numbers. Arrange them here so that the compound inequality makes sense, and your numbers are right. You know, if you've plugged them in backwards, you're going to get an inequality that makes no sense, because this number will be larger than this number, and you're going to go, wait a minute, that doesn't make any sense. Well, it's because you just need to move them. You just need to swap them. The numerators are the same, so it's easy to make that mistake. So just make sure that when you calculate one and the other, you just intuitively realize, oh, well, the smaller of these two numbers is my lower bound, right? It has to be, because everything else in the formula is the same. Again, how to form a confidence interval. This is a nice little flow chart on 296. Great little thing to have study ready. Then we're getting into the whole idea of hypotheses, type 1 versus type 2 errors. A type 1 error happens when you have rejected the null and assumed that the alternative was true, but actually the null was true. That's type 1 error. Type 2 is the opposite, when you have accepted the null when it was actually not true. Okay. Okay. Oh, this is helpful. On page, I even dog-eared this one. Page 315 right there. Common Z values for your alpha levels. These are Z values, so they're for large N, right? So, you know, for an alpha of 0.10, two-tailed, one-tailed, these are good to just have on hand. You always assume 95% or alpha is 0.05 if not otherwise specified. So that's page 315. Okay, what's a p-value? What's a p-value? Think about it. Either p is tolerable, which is within its bounds, or it isn't. I don't know how. There's a million ways to talk about this, but basically the p-value is just whatever's left outside of your confidence interval that you've chosen, because you've chosen the confidence level. So your confidence level is a personal choice, and then that determines this interval. And then everything that you've missed, everything that you've pushed out to the corners, that's your alpha. Okay, or excuse me, that's your p-value. Excuse me. Okay. This is on page 319. I like this little box down here at the bottom on page 319. Add that to your study list. Very handy chart to remember. 322. How to convert. If this is still hard to understand logically, this is how to convert two-tailed to one-tailed p-values. Okay. So now we're looking at hypothesis test. What's the difference between knowing sigma and unknowing sigma? Unknowing, not knowing sigma. What's the difference? only that sigma is replaced with S. We can do that and still get a Z value out of it because the numbers are large, N is large enough. But then I just like to remind myself of how one-tailed versus two-tailed, how I interpret those things. And this may seem a little abstract, hard to understand the importance of it, but just draw yourself a picture. And that's really the best thing that you can do.
Can I interrupt for a second?
Yeah.
On the last quiz, there was
Okay.
a question that had the hypothesis, the H0 being mu minus mu naught equaled like 27. And then the alternate being mu minus mu naught not equaling 27. And I didn't remember doing anything where it was a number other than 0. I really didn't know what to do with that.
Oh, well, well, I mean, really just, that's just saying the difference in the two is some other number. If I could look at the question, if you, maybe you can tell me which question it is, or I can just pull it up and look at it, and that'll give me more of a context to think about it.
Okay.
But I can look at it. You said it was on the last quiz?
Yeah.
Okay. 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 So, hypothesis test for small samples, okay? In the case of small samples, where either NP or NQ is less than 15, tests for a population proportion on the Z statistic may not be valid, which we would expect, especially when conducting one-tailed test. A test of proportions that can be applied to small samples utilizes the binomial rather than the normal distribution. These are called exact binomial tests due to the fact that the exact, rather than the approximate, p-value for the test is computed based on the binomial distribution. I don't know that we did any like that, but maybe we did. I'm sure that I highlighted this for a reason, and it's on page 342. I'm sure that I highlighted that for a reason. Maybe there's a question like that on the final. I can't remember. But the gist of it is, if you're small and you're doing one-tailed, you can use binomial, which is pretty cool. Okay, somebody tell me, because I wasn't in the Wednesday lectures unless I was giving it, did we do non-parametrics in class?
No.
Okay.
I think she took that out.
That's what I thought. That was our plan.
She
this
did
year.
in favor of the moment generating functions.
Right. Okay. Just wanted to make sure. All right. So that's that. We don't have to do that. If you're ever interested, they're very cool. Mainly because nothing has to be normal for it to work. Okay. We're in chapter 7 now. We're now comparing things. So this is a sampling distribution of two X bars subtracted from each other if you're comparing two different population means. This is for independent sampling. Okay, so let's look at this. So the sigma of the difference is the variance over n of each of them, summed and then square rooted. Okay. That's also called the standard error. Again, if it's large enough, then it's approximately normal. Here's a large sample confidence interval for a z. If they're known, you use them. If they're not known, you just use S. We can do that because n is large enough. Again, central limit theorem. Okay. It's the same format though. It's the point estimator, which is the difference in the parameter of interest, x1 bar minus x2 bar. So that's our core, that's our middle, plus or minus a critical z value times some correction factor. So this is a standard error, whereas before we were using the corrected standard deviation. Okay. We use the standard error here because it takes into account the fact that there are two things, not just one thing, that's giving us numbers. And, whoops, and then hypothesis tests here on 372. This is how you do the hypothesis test for these.
Alex, that's the formula that was for that question somebody was asking about. Their DO is not 0.
Okay.
Yeah.
Right.
Someone else had just texted me and said the same thing. And I was like, oh my gosh, I stared at that formula and like flipped out over it. Like I really got in my own head on the last quiz and just.
Okay. Yeah. So that's because you're looking at two different mu's. And if that number is not 0, then what that's saying is that you are expecting that the two are different by some quantity. That's what that represents.
Thank you.
Absolutely. Where does it define D0? Somewhere around here it defines D0, D0, but I can't find it. So 375. Oops. Okay. Confidence interval, 375. Right there. Confidence interval and hypothesis tests for mu1 minus mu2. This is using T. So how is this different? Well, we've got our same point estimator here and here. We're swapping out for T, critical T. We've got S squared, but notice that this S squared, I could just distribute this, right? And then plop it into this numerator and this numerator, and it would look exactly like the one for Z. But because we're in T land now, we've had to factor it out because this S squared is actually this huge mess. And it's not the S squared, not the regular S squared. It's this special S sub P, as they're calling it. This is like, this is how you deal with S squared. If you don't know sigma, this is how you deal with S squared if your N is too small. So, you know, our common problem is we have, if N is large, great. If we know sigma, great. That's like what would happen if conditions were perfect. Well, if N is not large enough, we fall back on T. And hopefully we still know sigma because then, you know, or we know that we can swap out sigma for S. Sometimes it doesn't work. This is why, this is a situation where we can't just flip-flop them because we're not dealing with one sample anymore. We're dealing with two samples and comparing two things. So that's why we've got to use this big corrected honker right here instead of just swapping one out for the other one. That's why we can't do that. Okay. Here's the test statistic for the same thing. Again, this S sub P is this big mess. And then in the numerator, we've got this D naught again, which is the suspected difference. Oh, right there. Yeah, the suspected difference, or whatever your hypothesis test is. Mu1 minus mu2 equals D. So if you were to set that equal to 0, then you're saying that you're expecting that mu1 and mu2 are the same, or at least you're testing that hypothesis. Okay. Oh, this is non-parametric again. Oh, never mind. No, it's not. All right, so when variances are unequal, this is on page 379. When variances are unequal, you deal with this in two different ways. If you have equal sample sizes, here's your confidence interval. Here's your test statistic for the difference being 0. And you've got this T is based on this crazy looking degrees of freedom right here. So you got to actually adjust your degrees of freedom. If you don't have equal sample sizes, okay, if you don't have equal sample sizes, this stuff changes just a little bit, because you've got now N1 is not the same as N2. So you've got it here, you've factored out the N, so you can plug them into their respective places. A similar treatment happens to the T statistic, but you're now you're doing the same thing to this V degrees of freedom. It turns into this huge thing, this huge mess, and that's what degrees of freedom you use for that T test. Okay. Now, if none of those conditions are satisfied, and if you don't have normality, then you have to go to Wilcoxon, which is a non-parametric, which we didn't learn about, but it's there, it exists, it's perfectly doable. Then we got into another way of comparing two population means. Instead of them being independent and we're just comparing them, we actually have paired differences. And these paired differences are where we're essentially gathering data on on the same observational units twice. We're doing a before and after picture. That's essentially what this is. That's a paired difference experiment. So you can't treat those data, individual data points, you can't treat them as just kind of part of the big pile, because the improvement or decline in between an individual unit that you observed before and after, that's important, right? If you were collecting, you know, let's say you worked for the IIHS, the Highway Safety Institute, that collects car crash data and how safe your cars are and making sure that cars meet certain safety criteria. Well, let's say that we tested a new Toyota whatever, and it scored, you know, this and this and this. We have the numbers for that. And there was a problem with that. We weren't happy with that. So we sent it back to Toyota and said, you have to make this better. So they did some stuff to it, right? And then they brought it back, and then we tested it again. We wouldn't want to know that it's just part of, you know, all new car data. We would want to know specifically that we're comparing the old data to the new data, because we're looking for an improvement, right? We're looking for the difference in those two. So pairing the data points is important if that's how your experiment is designed. Otherwise, you lose all of that detail about those individual experimental units from that before and after picture. So you've got a Z statistic here. It's calculated the same way as we've been seeing before, where you've got a point estimator plus or minus, critical Z value plus some correction. T is identical, just swapping out sigma for S, and even looking here that, even looking here between these two right here, okay, what's the difference? Nothing. We're just swapping Z for T. So what this means is that you can approximate, if you don't know sigma, you can approximate it with S, or you can be more conservative and go with S, yes, but then give it a T instead of a Z. Okay. Paired differences also have their own hypothesis tests. This is how you calculate those. It's the same kind of a thing. Here's the Z statistic. You're taking into account that testable difference. Conditions. By the way, that was on page 391. Sample size determination. This one also confused a lot of folks on the homework. So for equal sample size cases, excuse me, this is how you calculate what your N needs to be in order to get the standard, this sampling error that you're interested in. So again, we can use this R divided by 4 estimation for S if we need it. And the sampling error is what we're kind of like, that's how tight we want the numbers to be. So based on how tight we want those numbers to be, that will tell us how many people we need to talk to, or how many samples we need to take, or what N sample size needs to be. So let's think about how this goes. How does N and SC go related to each other? So sampling error. If we want the sampling error to be small, okay, this number is going to be small. Let me just write this down. This is how I see this. N goes as 1 over SE squared. So as the sampling error becomes small, because ideally we want really, really small sampling error, right? Well, we're taking a small number and squaring it's going to make it even smaller. So then 1 over that really small number is going to make N really, really large, right? Because these have to be in proportion to each other. So if this is small, then that's going to make this large, right? So you just think about that in terms of functional analysis. N goes as the inverse square. It's an inverse square, if that means anything to you. So N goes as inverse square of the sampling error. That's why we have to keep that in mind. This is how you use it to estimate for difference, for paired difference rather than the mu1 minus mu2. If you're doing paired difference, that's how you do this. So this is for mu1 minus mu2. This is for paired difference, okay? Because they're different. Ideologically, they're different. This is where everything in the first group is pooled together and everything in the second group is pooled together, and you're just calculating them separately and then taking their difference. This is the mu d. That's where you've paired the before and after, and each one is its own difference, and then at the end of that you take the mean. Okay. Okay, I've got one more little note back here. There's more non-parametrics. Anova. I think we're through the weeds now. Gosh, I certainly hope so, right? Comparing population proportions. Oh yeah, we can go through that too. All right, so Anova. Did you guys learn Anova? I think you did.
Yes.
Yes, okay. So Anova gives you an F statistic, capital F. Looks like this. Oops. F statistic looks kind of like this. Let me see if I can get a better picture of this. Oh no, guess not. Okay, so there's all these kinds of complicated, sum of squares for treatments, sum of squares for errors, mean square for treatments, mean square for errors. There's all this complicated kind of stuff. And what it boils down to is it gives us an F statistic. There we go. That's what an F distribution looks like. Kind of harkens back to a chi-squared, but it's more exaggerated. Okay, so what happens is you run an Anova to compare 3 or more means, and you should all know this pretty well. This is what your analysis project included. So you've got all of these different mu k means, and at least 2 of them are different than each other. Okay, your test statistic is the mean square of treatments over the mean square of errors. I have personally never manually calculated or made a student manually calculate an F statistic on a test. It's possible. You just do it like this. You just do it using these formulas over here. But that's just really kind of draconian. So we use a program to do it, right? You have a critical p-value. It's just the proportion that F is larger than that thing. This is a one-sided distribution, so you're always reading it from 0 and you're building up. It's cumulative going that direction. So that's why the p-value, the rejection region, is when the critical F value is larger than F of alpha, and the p-value is the probability that F is larger than that. So it's just wherever your cutoff is, it's just whatever's over in the tail, right? Here's a great example of, there's my table value, and then this tail over here that's shaded, that's my alpha. So you're just going one direction. There's no such thing as a two-tailed ANOVA test. They're all one-tailed. Okay. Conditions for ANOVA: random, normal, equal population variances. The normality assumption is less important than the variance assumption. Normality can be ignored. Oops, I'm not aligned here. Normality can be the second one. Normality can be kind of, yeah, okay. We'll get to you. You know, kind of pushed over to the side. If the population variances are equal, that's in the research or in the analysis project, that was what Levine's test told us. So as long as you're getting number 3 and number 1 satisfied, number 2 can be kind of like, you can fudge it. It's okay. Okay. So we did that. Did we do population proportions? Wait a minute. I know that we did. We already did this. Comparing 2 population proportions. Did we get into chapter 8? Tell me if we did or did not. I'm thinking no.
We did chapter 8.
I'm sorry?
We did have chapter 8, I think.
Okay, great. Well, let's go through it real quick.
We went all the way to 9.
This is the same thing, but now we're just comparing to proportion. We're comparing to p-hats. That's all that is now. So we have p-hat 1 and p-hat 2. Same kind of treatments as before. This is a sampling distribution of the difference of the p-hats. The mean is just p1 minus p2, the expected value. And here's the sigma, same kind of a thing, PQ, and of course Q is just the complement of P. A large sample CI using Z. Okay, let's break it down here. Let's talk about the structure. I got to talk about the structure. So what have we got here? We've got the difference in the p-hats, plus or minus. We've got Z. And then under this, well, that's just the standard deviation over here that we just looked at. Same kind of a thing. You can approximate it with, what are we approximating with here? We can approximate the P and the Q with P hats and Q hats if needed. Okay, test statistic right there. I don't try to commit all this stuff to memory because, you know, that would be insane. If you understand how it's used, then, you know, that's what's important. Hypothesis test. This is how you set up the hypothesis test. You can use P hat here and Q hat if you need to, if you don't have P and Q. And the rejection regions behave exactly the same. It's just less than the negative value or greater than the positive value of the critical value, C alpha. P-value is just the probability you're greater than that. So you're just looking again at that area, the curve, under the curve area, either higher than the top tail or lower than the bottom tail. Okay. Two-tailed test is exactly the same thing, but you just got twice of it. You got one on each side. Sample size, same kind of thing. Notice that N still is an inverse square relationship, just as it was before. And this is if N2 and N1 are different. So you just have some if N1 and N2 are different, then you have some A ratio factor, scale factor is essentially what it is. And you just incorporate that scale factor into the denominator and then into the first of the P1 and P1 Q1 right here, because A is the scale factor applied to N1. Okay, so just a little adjustment. Multinomial experiments. Oh yeah, I remember doing this now. Multinomial experiments. This is like a binomial, but multi, right? Multiple outcomes. So H naught is that all three probabilities are the same, no preference. HA is that one exceeds a third. Of course, they have to all sum to one. So if you're saying, well, maybe one's less than a third, well, then yeah, but another one, if you shrink one of them, another one's got to grow, right? Because it's still got to be, everything together has got to be one. So I think there was like a fossil question or an art exhibit question like this in the homework. I think it was something like that. You run a chi-squared test for this, where you just have the number in that one group minus the expected value. If they're all three the same expected values, you just have the same thing in all three of them. Okay. So that's this is for the chi-square test. Yeah, of course we did this. I don't know what I was thinking. This is for the chi-square test. Your chi-square statistic is just this sum, like I just talked about, with the n minus the expected value, quantity squared over the expected value again, and you sum them all up. That's your test statistic. Go to a chi-square table, and then you can compare them. P-value behaves exactly the same way. Rejection region behaves exactly the same way, still having k-1 degrees of freedom. Okay. Notice that the n times p for that cell, if this is all in a table, the expected number of outcomes of type I, assuming that H naught is true, that's the expected cell count, okay? The expected value. That's what you would expect to be there. So looking at this, this is an example of like how many that were there. Here's 50, 50, and 50. That would be evenly distributed across 3 groups. But here's 61, 53, and 36. That's what, you know, we've instead of having 3 equally filled bins, we've got one that's really tall and one that's not, and one that's even lower. So that's what that means. Two-way contingency tables, this is the same thing, but for running it 2 ways. So the E of the IJs is this R value, R times C, and where is R and C? Oh, right here in front of me, good grief. R is the total for a row, CJ is the total for a column, and N is the sample size, so you just run that in. And it sounds a lot more complicated than it is, but you know, you've got all these numbers in here. You've got, I don't know, 1, 2, 4, 5, 9, 10, 11, 1, 1. All right, so these are your I's here. These are your J's. And then you've got just a total row. Total row and total column. And so you just run down here, 1 plus 5 is 6. Gives me 17. That's 11, 12, and 15, you know. And then you do the same thing going across. 7, 24, and 11, 12, 13. And then, yeah, right. So that's how, that's what it's saying. These are the RIs. These are the RIs here. And then these are the CJs, CJ, CJ. That's all that is. Two-way contingency table, meaning that we're going 2 different directions here. That's all that is. Everybody got that? I hope so. Cell counts behave the same way. Expected counts, excuse me. And the test statistic behaves the same way. You've just got the N and that IJ minus the expected value for that IJ divided by the expected value. And those are the same E, the E of the IJs. That's what we just talked about there. Okay. Oh, yeah, that's the picture that I just drew. All right. Very good. I should look ahead sometimes. And the reason that you would do this 2-way contingency chi-squared business is if you're trying to determine if there's a relationship between 2 different parameters. That is what that is for. Wonderful, huge flow chart on 487. Good to look over. I think that's it. All right. Did we do chapter 9, the probabilistic, the linear regression?
She sent us a video.
I'm sorry?
Yes, she sent a video.
Oh, okay. Okay, great. So do you want to go over any of the linear regression stuff? I'll leave that up to the room here.
I say yeah, if you don't mind.
Sure, yeah, happy to do it. So a lot of this is linear regression, right? We're talking about lines. We're talking about y equals mx plus b. But, of course, we've just renamed everything to make it more confusing than it was before. So what is happening whenever you do any type of regression is you are picking a line or a function and you're taking your data points and essentially just moving them, you're shoving them onto that line and looking at how far each data point had to travel to get there. That's called a residual. So the less distance each data point has to travel, the smaller the residual, the more well-fitted your data naturally is to that line or curve or function from the get-go. The farther each data point has to travel, the farther away from that model of perfection your data is, okay? Linear is a common type of regression. Looking at a QQ plot, essentially what a QQ plot does is it regresses your data to the normal curve. Not really, but that's basically what it's doing. You can regress to whatever kind of thing that you want. Okay, so there is in statistics, the formal nomenclature that we use for this is that the line don't look at that, the line that we are regressing to is the deterministic model. Okay, that's the deterministic model. It allows us to predict or determine where a data point should be if conditions were perfect. But then our data points are not perfect. They're off of the line. The random error is what has caused, we say that that's random error that has caused our data to deviate from this model that we are assuming is perfectly deterministic. Okay. So look at this. We've got y equals deterministic plus random error. I want you to think of this as being very, very similar to y equals mx plus b, right? We're all familiar with that. So this is essentially the line that we're talking about minus the random error. It's minus or plus this distance in between right there, okay? So I'm talking about just like this right there. That little distance right there, okay? So to fit a first order or a straight line, first degree, if you will, first order straight line probabilistic model, you're going to get y equals beta naught plus beta 1x plus epsilon, where y is the dependent variable, which we know very well at this point, x is the independent variable, and then b naught or beta naught plus beta 1x is the deterministic component. So that is where your mx plus b comes in, mx plus b. So beta naught is your y-intercept, and beta 1 is your slope, okay? That's what we're dealing with here. So the only thing that is added, so this is effectively what I'm saying. This is what I'm saying. This is identical to saying y equals b plus mx plus error or residual, whatever you want to call it, okay? So this is something you should feel very familiar with. And then the error is just that little distance that we had to travel there. Boop, 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 boop. Okay. And I really should look ahead again. If you don't believe me, it's right there at the top of page 503. So there it is. Okay. All right. We also call that deterministic component, beta naught plus beta 1x, we call that the line of means, because if we were to average all of these random errors, all of these little tiny epsilons here, we would actually get a perfect fit like that. So that's what would happen if we averaged all of those errors. That's why we call it the line of means, because it's the line that goes through all of the means. Okay, so, okay. Least squares approach. Most common way to fit a line, a straight line. The least squares approach, you have your x and y values. You get this y tilde, which is -1 plus the x value, just shifting it. Take y minus y tilde and then square it. That's your sum of your errors. This is your errors. This is your sum of your errors. Or excuse me, this is your errors, sum of errors. Sum of errors squared. That's all you're doing right there. These are your errors squared, sum of errors squared, which we call SSE. Okay. And then how do you do that? Well, oops. So there's the real formula for that, for SSE. Okay. And then, so we're taking, so where's the, did I skip the sum of squares? Wait a minute, I think I went too fast over here. Nope, I didn't. Looking for where the sum of squares is defined. Oh, man, it's right here in front of me. All right, so the slope, which is that beta 1, this is the sum of the squares of the xy's over the sum of the squares of the x's. That's should look identical to, you know, what you're used to seeing as what's the slope? Change in y over change in x. Look at that, same thing, right? Y-intercept is simply the y bar minus the beta 1 x bar. That's just the y-intercept. The sum of squares, you go through this whole thing. Each individual data point minus x bar, each individual data point minus y bar. Here is a more common or more helpful or more useful way to calculate it. When I'm doing it, I do it using these here. That's the top, that's the bottom. I use those because they're just a lot quicker to do. You can just sum everything, divide by n, subtract from the sum of the products. You know, same thing here with the x-axis. So I use these on the far right. I can even, maybe not. Well, I can't find a highlighter right now, but I use these. For my S, sum of squares right there, I use those. A lot faster. Okay. I'm on page 507 if you're keeping up. This is important. And I'm pretty sure, I know I've put this as a trick question on a test. Not really a trick, but it definitely tricks you if you're not paying attention. The model should be interpreted only within the sample range of the independent variable. So if you have collected, the independent variable is the x-axis. So if you have collected data, and there's your data, okay? Maybe I'm gonna make this easier on myself. I'm gonna erase a couple. Okay, those data points never existed. All right, so what this is saying is that my data, my actual data collections, again, this is independent variable here, right? My data collection exists over the domain, good algebra word, the domain of there to there, right? That's my, this on my x-axis, that's my domain. So that's the only place that I can use my model to predict an outcome. So, you know, it would be reasonable to assume that I fit something, I don't know, linear, I don't know, something like that, right? That's about, looks like my residuals are about evenly balanced. So something like that would be my line of best fit, my trend line, my least squares line, regression line, whatever. So if I take that line, and let's say that line is, I don't know, y equals, what's a good estimator? 0.4x plus 1. I don't know. I'm just making this up. And I go, okay, I have a model. I can predict any y value you want. Give me an x value. This linear equation, sure, it exists over the whole real numbers. But as a deterministic model, it only works from this x1 to this x2 value. So anything in the middle there between x1 and x2, I can put in for my x and get a reliable y value out of it. But if I plugged in something from way up here, maybe I plugged in x3 from way up there, I may want to know what the model says about that x value, but too bad, so sad, I can't use my model because I didn't collect any data up there. So I have to only use my data to predict stuff that happens in between the data that I've actually collected. Otherwise, there's nothing out here. There are no invisible data points out here to support the model even does that. It may totally be the case that as soon as I pass that x2, that all of my data drops down here to the bottom. I don't know. Maybe there's some mass attenuation of the, you know, something. I don't know what it is. But at that point, the trend line really needs to drop down. And in which case, you know, if I'm just do along, do up here, look at that. That is not even close to where my data actually is because I didn't collect any data up there. So you can only use the model to predict in between what you actually have data to back up is really going to happen. Okay, so I know I've put that on a test before. Worth mentioning. Page 519. Oh yeah, this is really, so each of these residuals, guess what, is also normally distributed and has a probability distribution of its own. It may not be normally distributed, but it has a probability distribution and behaves just like any other probability distribution that we've gotten. So that's pretty cool. Sigma squared, estimation of sigma squared is again S squared, but we've got our SSE, which we talked about before. We just do n minus 2 degrees of freedom instead of n minus 1. Same thing, same type of adjustments here for S. Of course, S is just the square root of that. So I don't even know why they would put both those lines in there. And we already knew this. We already knew S of the YYs. We could have calculated that from the last page I showed you where I highlighted the pink. All that is the S sum of squares of the YYs, and I'm just squaring the Y's rather than doing X and Y, just like I did the sum of the squares for the XX's. I'm doing YYs here because I've taken this, see how this is a normal curve on its side? Well, all I did was this. I just flipped it 90 degrees, and now I've got it in XX format, but Now it's in YY format. So that's all that means. Making inferences about the slope. Sampling distribution, again, here's a sampling distribution. Beta 1 has its own sampling distribution, and it's just the standard deviation is sigma over the square root of the sum of squares of the x-axis. Estimate it with S again. That's called the least square slope. T statistic, we really don't use Z. Z is just too, it's too bold. It's not conservative enough for this application. So we would just use T for this. So there's no Z test statistic for this model, for this application. You're not going to see another, I don't think they would have put it in here. No, we just use T for this stuff. So you have the beta 1 and the hypothesized value over S. Here's what your S is again. It's that S over the sum of squares, XX square root. Hypothesis test. The rejection region and the p-value behave the same way. That's what's important, because if you're going through, if you're looking at something, if you're just looking at a report or something, all you need to look at is to go to find the p-value. Find the p-value, and you can interpret the p-value the same no matter what. That's why that's really the punchline of everything, is what the p-value is. Okay. Correlation coefficients. This is the gravy. This is the gravy on top. Okay. Correlation coefficients. This is for any bivariate relationship. Okay. Correlation is a percentage, is a proportion of the strength of the relationship between the two bivariations. So a lot of times, so in a QQ plot, you can look at the residual values, the residual correlation of the QQ plot. That's helpful, because when you're looking at the QQ plot and it has essentially taken your data and regressed it to a normal curve, what that does is it tells you how normal your data is. But in order to really interpret that, so you're not just trying to, rely on your eyesight to tell you how close these dots are together, right? Because that's subjective. Looking at the correlation from the QQ plot will give you an actual number that you can think of as being like telling you how normal your data is. The same thing can be done here for this linear regression. Your R is your strength of your relationship between the two variables, and that's not up to you to interpret. It's just a calculation. Here it is. Okay. The S-X's, the S sum of squares in the XY's and the X-X's and the YY's are the same that we've had before. These are all exactly the same here. But relying on a single calculation, R, rather than glancing at a bunch of dots on a screen and trying to say, oh, how strong of a relationship is that? Relying on R is a lifesaver. Okay. Again, you have a test statistic for this. Awesome. One tail test, two tails test. T, the critical T value, and the P values, again, oh, excuse me, again behave the exact same way. Okay. R squared is called the coefficient of determination. And the practical interpretation of R squared. So the R square percent of the sample variation can be explained by using X to predict Y in the straight line model. So that's what that's telling you is how close to being linear, or in the case of a QQ plot, how close to being normal, your actual dots are. How much of that can be explained by that? That's just a percentage, right? So that's all that is. And then using this to predict stuff, again, I don't even try to memorize these things because they're just, it's just, I don't see the point. 542 and 543, you've got 4 boxes I would recommend looking at. Figure out why you would need them so that when you're going through a question and you're going, oh, I don't know what I even need to do here. Just stop and think about the type of question, what the question's asking you, try to dissect it, and then figure out, oh, well, I just need this, or I just need this. Or at least you'll know, and your brain will tell you, oh, wait a minute, I know this is this mean value confidence interval. Oh, I've seen that. I just need to go look at the formula for it. Okay. We did not do nonparametrics. And that's it for chapter 9. And that's it for the book. So questions for me before we switch over to this game called Guess My Test.
Do you know when the final is going to be open and when it's going to be due?
I don't, but I can find that answer for you in just a minute. Let me look.
She had also said that she might decrease the number of questions that were going to be on the final because it was pretty high at one point. Do you know if that's happened?
Mm-mm. None of that is, that's all beyond my purview. I know that the final, I believe, used to be 60 questions. And as far as I know, that's what it still is. But I didn't know that there was a discussion about it being changed. So let me look at the syllabus real fast and look at when they...
According to my Stat Lab's calendar, the exam goes live on the 7th and is due on the 11th.
Okay. Then that's what we would go with. Syllabus, okay. 7th to the 11th sounds right. I'm just gonna scroll through. Yeah, May 7th, it opens at, let me just share this here. So it opens, I'm down here. It opens May 7th at midnight and closes May 8th, that should say May 11th. It says May 11th in my stats lab, right?
Yeah, I think it was originally only going to be open the 2 days, and then a bunch of people had questioned if she could extend that at all, and
That's right. Okay.
Stretched it out to the 11th.
Okay, so this just has not been updated. So go with whatever's in my stats lab, because that's the computer system that'll determines that. Okay, so let's go into. And as in terms of the questions on the final, I'll check really quickly and see what it's at. Final exam. So yeah, it starts the 7th at midnight, ends the 11th at midnight, or 11:59. And it covers all the chapters. I can't see how many questions are on it actually. I can see where I click on that, but it's grayed out for me, so I can't open it up. So sorry about that, but I didn't know that that was even on the table, so don't rely on me to answer that accurately. Okay, so let's go into this game, which is pretty cool. Now, I have this as a document, and we're going to do this together, but I have it as a document with the solutions, and I'm going to send the whole thing out after we finish up here tonight. So it's you'll have this as a resource. But I didn't want to send it out ahead of time because we're just going to be doing it together. It'll be nice and fun. So let me pull this up here. Okay, so here's a nice little chart that just to summarize the different tests that we learned this semester. The only thing we did not do were these non-parametric tests. There's one for median, there's one for a large independent samples, and then there's one for small samples. So you can just ignore those. They're in your book. Independent and dependent, excuse me. There's an independent Wilcoxon and a dependent Wilcoxon. All right, so we've got z-test, t-test, proportion, chi-square. We've got independent z, dependent z, same for t, F statistic, chi-square, goodness of fit, chi-square, that's for one scale, chi-square independence. That was the binomial, or excuse me, the bivariate here, looking at two different relationships. So I'm going to give you a scenario, and you have to tell me what the test is. The National Center for Border Security and Protection has developed the Embodied Avatar, a kiosk with computer-animated border guard that uses our AI to scan passports, check fingerprints, read eye pupils, and ask questions of travelers crossing the U.S. border. Based on field tests, the manufacturer claims the avatar can correctly detect deceitful speech 75% of the time. The Border Patrol performed their own trials in a large sample. Is the manufacturer's claim correct? So I want to know what kind of test I would do and why I would do that test. What do we think? Just speak up whenever you're ready to share.
Well, since it's large, it has to be a Z.
Right, it is Z. What are we going to do with Z?
I haven't worked that out yet.
Well, think about what's the parameter of interest here. What are they claiming?
75%. So is that a proportion?
It's a proportion, right? So we're trying to check and see if their proportion claim is good or not. So it is a one proportion. It is a one proportion z-test because it's a large sample and it's large enough that we can show that NP is greater than 15, NQ is greater than 15. Independent dependence not applicable because we're just looking at a proportion. We're just calculating a reliability. So on the calculator, we would use the one prop z-test. Okay. An international team of economists investigated the possible link between IQ and birth order. The data source for the research was the medical birth registry in Norway. It is known that the mean IQ for all Norway residents is 5.2 points. In the study, a sample of 581 Norway residents who were sixth born or later in their families had a mean IQ score of 4.7 with a standard deviation of 1.8. Is this sufficient evidence to conclude that the mean IQ score for all Norway residents who were the sixth or later born child in their families is lower than the country mean of 5.2 points? So this is saying if you were the sixth child or later, is your IQ going to be lower than the mean of the country? So I'm not asking you to calculate this. I'm asking you to identify what would I do.
The x squared GOF.
Chi squared? No.
Okay, then I'll go with my first answer.
Okay. Which is what?
2 proportional z.
So what's our parameter of interest here? Always define your parameter of interest first. Are we looking at a proportion?
No, we're comparing two things. Okay, so it's not that either. Okay.
Well, we're not really comparing two things. We're looking at one thing and seeing if it meets a criteria or not. So what was the data was collected on whom? Where was the data collected? This is the only data that was collected, right? We are just told that the mean of the country is this, but that's like a separate, well, that's really dark. Why would you want to highlight something that dark? Let's try that. Okay, that's just something we're comparing it to, but we're not comparing to. We haven't collected a mean, a country mean, and then we've collected these 6 children means.
Okay.
So what are we actually doing here?
Are we hypothesis testing where I lost it. Something where we're comparing the two because we want to know if it's going to be less than that given one of the 5.2.
Well, yeah, you can say that, but then, sure, but then what actual calculation are you going to do? What's your test statistic in this case? You can set it up as a hypothesis test, sure, but what's the test statistic? What are we going to calculate to confirm or reject that hypothesis? How many populations do we have? One population, right?
Mm-hmm.
Is it large or small?
Large.
Okay. What's our parameter of interest?
Their IQ.
What type of IQ?
The 6th born or later.
Yeah, but what's the parameter of interest? Is this sufficient evidence to conclude that the mean?
So we need a P.
Well, I mean, we're getting too far here. the parameter of interest is a mean. We're asking a question about a mean. We're not asking a question about a proportion like we were in the last one. We're asking a question about a mean. So this is just a simple z-test. We have n, we have 4.7, we have a mean, and we have a standard deviation. We can just run a quick z-test on this. So this is just going to be one population, large sample, mean. The test statistic is z, and on the calculator we just use a z-test.
And you said you're going to share this with us after we go over it?
Yeah, I'm sending this document to everybody, yeah.
Okay, thank you.
It just has the answers on it, and, you know, I'll send it to you afterwards. Okay, so a study of adults who completed a dental anxiety scale test was reported, and the scale ranges from 0 indicating no anxiety to 25 indicating extreme anxiety, teeth biters. The data show a mean score of 10.7, standard deviation 3.6, n is 15. Does this show a difference from the target population mean of 11?
The t-test?
Is a t-test, right? Why?
Because we have 15 adults.
Right, small sample. How many populations?
It's just one population.
One population. What's our parameter of interest?
The mean score for the anxiety level.
Mean, right? The other reason we need to use T is that what do we not have here? What do we not? What's unavailable?
Population standard deviation.
Sigma.
Yeah, sigma.
Perfect. So this is just a t-test. It's what they do a lot of at the Lipton Company. Analytical chemistry presented research on a new method by GlaxoSmithKline to determine the amount of drug in a new tablet. Drug concentration as a percentage is for 50 randomly selected tablets are provided in the table. Standard method of assessing drug content yields a concentration variance of 9. Can the scientists at GSK conclude that the new method of determining drug concentration is less variable than the standard method? So what is our parameter of interest here?
Variance.
Good, variance. We're not asked for a mean, we're asked for variance. Is less variable. That's the key word right there. That right there tells me that we're doing something with chi-square. Something with chi-square. And this is a so this is a chi-squared test. Is it a small sample or a large sample?
Large.
I would even say that this is maybe a small sample, but I mean, it doesn't really matter with chi-square. But you just use the chi-square formula on page 348 to calculate the test statistic. And that's it. In this journal, a study of memory using free recall was reported for 8 participants. The participants memorized a list of items using a category clustering strategy. And then researchers at Central Michigan developed a category clustering algorithm for computing the measures. One measure called ratio of repetition was recorded for 8 participants in the memory study. These ratios are in a table. Is there sufficient evidence that the median ratio of repetition? Oh, you know what? We didn't even do this one. This is one of the non-parametrics that we didn't do. So we can skip that one. All right. Yeah, this one will work. A study of the differences in cognitive function was published. Total time spent on the trial-making test was used to measure cognitive function. Okay. Researchers theorized that the mean time on the test will be larger for schizophrenics than for normal subjects. The data samples of 41 schizophrenics and 49 normal individuals and yielded the following results. So what kind of test are we doing here? How many populations do we have?
2. Is it a 2 sample Z test?
Yes, it is. It's a 2 sample Z test. Why?
Well, I got 2 different groups.
Okay. So
And
why is it not paired differences? Why is it not T?
Good question.
So answer them.
I'm trying.
Why is it not paired difference? These are schizophrenic people and normal people.
Yeah, because they're completely different.
Right. They're totally independent. Yeah, totally independent. No attempt to pair them. And why is it Z and not T?
Because of the number of people.
Yes. Good. What's our parameter of interest here? What parameter of interest are we comparing?
Mean.
Mean. Perfect. Love it. Yay, we're getting warmed up now. Make sure I can do this one. Yep, we can do this one. Children's recall and recognition of TV adverts was found in this journal. 2 groups of children were shown a 6-second commercial for Sunkist Fruit Fun, whatever that is. The first group was the AV group was shown the ad with both audio and video. The second group, the video only group, was shown just the video. So the idea is that if you're watching a commercial, just watching it with it muted, do you get the same impact as if you heard it also? Okay. So essentially, if assessing the effectiveness of muted commercials versus audible commercials that you can hear and see both. Each group had 20 children. For the viewing, the children were asked to recall 10 specific items the ad had. The researchers theorized the children who received an audiovisual presentation will have the same level of mean recall as those who received the visual only aspect. Okay, so what are we doing? So these were different kids.
Would it be a 2 sample t-test?
Yes, why?
Because it's not paired difference because there's no attempt to like pair the data.
They're independent, yes?
It's a t-test because it's 20 children, so that's less than 30.
Yes, small sample. What's a parameter of interest?
A mean.
Mean, and we're comparing means, very good. So it is indeed a 2 sample t-test. Camp Jumpstart, is an 8-week summer camp. Counselors developed a weight management program. It centers on nutrition, and education, and physical activity. The study was published in Pediatrics. The BMI was measured for each of the 16 campers. So what are we doing?
I know this one's paired.
2 paired difference T.
Right. Paired difference t-test. So because they're paired differences, what do you have to do first?
Like do that, subtract the columns.
Right. Make a column of the before, a column of the after, and subtract them and get those differences. And then that's the data you're working with. Does that make sense?
Yes.
Perfect. Love it. Okay, this one is a Wilcoxon. So I'm just going to skip that one. Wilcoxon's also called a Mann-Whitney test. I don't know Wilcoxon published it, but I think Mann and Whitney, I don't know, whatever. But Wilcoxon published it, so that's why it's called Wilcoxon test. This was like back in the 30s. So this one, oh, this is also Wilcoxon. Okay. Here we go. Here's a good one. Dermatologist's primary recommendation to prevent skin cancer is minimal exposure to the sun. Duh. Yet models used in product advertisements are typically well tanned. Yes. University of California and California State researchers designed an experiment to investigate this phenomenon. 56 college students were randomly assigned into one of 3 conditions. View the product advertisement features models with a tan, view product advertisements featuring models without a tan, and view product advertisements without models. The objective was to determine whether the mean attitude towards tanning differs across the 3 conditions. So what do we do?
Would it be Anova?
It is Anova. Why?
You've got 3 different groups.
Yes, and what is our parameter of interest?
The mean attitude.
Mean, very good. So what's our test statistic?
It's an F.
F, yes, my favorite one. So we have how many populations?
It's 3 populations.
Right. Is it large or small?
We
don't really know because we don't know how many people.
56.
56, yeah, I would consider that large.
Large.
But we don't know how many of them got put into each group, but still, large enough, right?
Mm-hmm.
There you go. National Grilling Month. We can do this one. We can actually do all the rest of these. Good. So I skipped all the Wilcoxons. All right, July is National Grilling Month. Wait a minute. A Harris poll reported on a survey of American grilling preferences. They want to know the difference between Democrats and Republicans. I forgot about this. When asked about their favorite food prepared on a barbecue grill, 662 of 1,250 randomly sampled Democrats preferred steaks, as compared to 586 of 930 randomly sampled Republicans. So what do we do? Other than give up and go home?
This would be a proportion test, right?
Yes, proportion, because you've got p-hats. You've got a p-hat, there's a p-hat, and there's a p-hat. All right, so you got how many p-hats?
2.
2. So what are we going to do with them?
A z-test.
It's a z-test for what is their parameter of interest here? Not means. We just said it. We've got p-hats, so we're going to compare them.
What proportion?
Binomial something something?
Not binomial, no. This binomial is only when each outcome has 2 possibilities.
The proportion that prefers steak?
Mm-hmm. So we're looking at a proportion difference. This is the P1 hat minus P2 hat, not paired differences, because obviously these are independent groups, right? No pun intended. But we're looking at a proportion difference, okay? And it's a z-test. So this is a 2-prop z-test, 2-proportion z-test. They're proportion it's a proportion difference, but not paired proportion difference. Myocytes, whatever, are mushrooms with slime molds that are food source for insects. I know nothing about biology. Results were published in a study that investigated which of 6 species of slime molds are most attractive to beetles in a rainforest. A sample of 19 beetles feeding on slime mold were captured. The species of slime mold that the beetles were eating was identified for each beetle. So they captured the beetles, captured the slime mold. Hint, hint, right? We're looking at, I realize I look like some kind of a ghost or something with this stupid light this bright. There we go. So we're capturing beetles and we're capturing slime mold. Hint, 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 right? Researchers want to know if the relative frequency of beetles feeding on slime molds differs for the 6 slime molds.
Anova?
Anova is for comparing different means, multiple means. The researchers want to know if the relative beetle frequency differs for the 6 slime mold species. So we're looking at 2 different kinds of categories because neither beetles nor slime mold, and neither of those are numerical, right?
I think what threw me off is the 6. Do I care about that or no?
Yes, 6 is important.
Okay.
So how do we go about comparing the relative connection between 2 types of categorical data?
Paired difference?
For numerical, yes, not for categorical.
Well, I'm striking 0 here.
Because neither of these parameters are numerical. We're looking at beetle type and slime type. So it's near the end of the book. Very, very, very end.
Are we going to do some sort of linear regression?
Nope.
Oh.
Nope. I'm just looking for
You
the
said end of the
relation.
book. I was
I
like,
know, that's what I was saying. Like,
Well, not quite that far.
I haven't done that homework yet, so I wasn't sure.
Not quite that far. Back up 1.
So whatever we did in chapter 8.
Yeah.
I hate chapter 8.
Hang on, let me look at my notes.
We got 2 different types of categorical data. We're wondering if they're somehow intertwined.
Chi-squared?
Chi-squared, which one?
Hey, I pulled that out. Somebody else can go on.
It is
Go 2 sample because there were 2 things.
Yeah, so what do we call that?
Oh, I don't know. 2 sample.
Goodness of
Is
fit.
that the GOF one?
GOF, yeah, GOF. Yeah, that's right.
Woo!
Yeah, because GOF allows you to GOF allows you to look at the intersection of those 2 variables. All right. Good job. So you have to put those data into lists in your calculator and do just a GOF test on the calculator. Major, again, this is the kind of thing I've never done it by, well, I've done it by hand. I never want to do that again. It's just too tedious. Major newspapers lose credibility, et cetera, et cetera, et cetera. Certain types of stereotypes are more often in deceptive news stories than authentic news stories. They analyzed N equals 184 new stories proven to be deceptive, 128 that were proven to be authentic. Researchers determined whether each story was neutral, negative, or positive for each tone group for deceptive and authentic. So we've got deceptive and authentic, and then under each of those, you've got neutral, positive, or negative. So what do we have? Is it categorical or numerical?
Chi-squared with the matrices?
Yes, exactly. Chi-square in a matrix. That's just a regular chi-square.
All right. I meant to say that.
Yeah, chi-square with the matrix. That's a regular one-way chi-square test. Basically what that's doing is it's taking your data and then it's just running it through the calculation and giving you another matrix as your output that are the expected values, essentially, right? And it gives you a p-value comparing the 2. So, all right, cool. That's it. Any questions for me? If you, of course, as always, please email me. I try to get to emails within 48 hours, every email. So if you think of something else you want to ask me about, just let me know. Send me a screenshot. Screenshots are helpful if you're somewhere in my stats lab, because then I can look at what you're actually seeing rather than just my numbers, because if I go in and generate the question, I'll get different numbers. So taking a screenshot of something that you're having trouble with in my stat lab is very helpful.
This game was helpful. Thank you.
Oh, I'm glad.
Thank you.
Yes, thank you for all your help this semester.
Happy to do it. Pleasure's all mine.
And you're going to post this, you said?
I'm going to email it to everybody right now. I'm just going to email it to the group.
Thank you.
Thanks.
Okay.
Good night.
Good night. Hit me an email if you need me.
Thank you.
Can we ask you questions on the final or no?
Try me. I'll plead the fifth if I have to.
Thank you.